When you watch a vehicle moving at high speed abruptly crash into a barrier, the physical reality is chaotic. The metal crumples, the tires skid, and energy scatters in all directions. Our brains naturally track the entire messy journey involved in bringing this mass to a halt. But physics requires precision that human intuition cannot provide. To analyze kinematics, we have to strip away the erratic, path-dependent physical journey. Instead, we must replace it with a rigid mathematical state vector, a direct line pointing from where an object was to exactly where it is right now. This requirement leads us to a specific mathematical destination. By the end of this analysis, we will map out the exact equation for instantaneous velocity, v equals dx over dt. To get there, we have to separate simple scalar measurements from precise vectors. Then, we will map constant rates of change algebraically. And finally, we will use the limits of differential calculus to solve for motion in a single frozen instant. True kinematics does not care about the human experience of traveling from point A to point B. It requires mapping absolute mathematical state changes. Look at a cross-country skier pushing across a course. If we track their motion using distance, we are using a scalar quantity. Distance simply tallies up how much total ground the object has covered, completely ignorant of the direction it is traveling. If the skier moves forward 180 meters, turns back 140 meters, pushes forward another 100 meters, and so on, their scalar distance simply adds those numbers together. The total ground covered sums to exactly 420 meters. If we reevaluate that exact same motion using vectors, the math changes. Because vectors track direction, the backward-leftward movements directly subtract from the forward-rightward ones. Those opposing directions mathematically cancel each other out, leaving us with a net result of 140 meters to the right. This resulting vector is called displacement. Displacement is the strict measurement of a state change. It ignores the path taken and asks a single question: how far out of place is the object from its original starting point? The contrast between distance and displacement becomes absolute when an object finishes its motion in the exact coordinate where it began. When racing Indianapolis 500, they have traveled a scalar distance of 500 miles. But because the final position coordinates perfectly overlap with the initial position coordinates, those vectors cancel out entirely. The total kinematic displacement of a winning car is precisely 0 miles. This direction awareness is a non-negotiable requirement. If we build our formulas using scalar distance instead of vector displacement, the kinematic equations that follow will output incorrect data. Once we have an accurate measurement of an object's position, we need to know how quickly that position is shifting. We transition from measuring static displacement to measuring how velocity changes over time. That rate of change is acceleration. This is a Cartesian velocity time graph. We can use it as a geometric tool to visualize acceleration. We plot a car in an initially stationary state, 0 meters per second at time 0, and then plot its final state, hitting 10 meters per second at the 2-second mark. By drawing a straight line between these two states, we can extract the algebraic slope. We apply the formula for constant acceleration, a equals final velocity v minus initial velocity u, all divided by time t. 10 minus 0 divided by 2 yields a constant acceleration of 5 meters per second squared. But this algebraic method has a fatal limitation.
Finding a slope by connecting two static points is only mathematically valid if the object's acceleration is perfectly constant. Real-world physical forces constantly fluctuate. Friction, drag, and engine output vary from millisecond to millisecond. To accurately map reality, we require a mathematical framework capable of handling continuous variation, rather than relying on straight algebraic lines. This chart represents a displacement time graph tracking an object under variable acceleration. Because the acceleration fluctuates, the geometric representation is no longer a straight line, it is a curve. If we calculate the average velocity between two distant points by drawing a straight secant line across this curve, we end up with delta x over delta t. But this average ignores the dips and spikes of the actual path. It fails to capture the true speed of the object in real time. To fix this, we introduce the core mechanism of differential calculus. We take the time interval, delta t, and begin shrinking it infinitely closer to 0. As the two coordinate points slide together, the secant line collapses, morphing into a tangent line that touches the curve at only one distinct point. Instantaneous velocity is defined geometrically as the exact slope of this newly formed tangent line at that specific mathematical coordinate. Mathematically, we define this by applying limit notation to our average velocity formula. As delta t approaches 0, delta x over delta t transforms into the formal derivative, dx over dt. We are dividing a microscopic change in position by a microscopic change in time. Applying this infinitesimal limit allows us to isolate the exact speed and direction of an object at an instant that effectively lasts 0 seconds. Here we have a polynomial position equation representing a real-world object's movement. X as a function of time equals 6t squared plus 8t plus 7. By applying the power rule of differentiation to this function, we drop the exponents and multiply. This generates an entirely new equation built strictly for measuring velocity. Our derivative function, dx over dt, equals 12t plus 8. We now have a functioning velocity formula. To find the exact state of the object at precisely 3 seconds, we simply plug 3 in for t. 12 times 3 plus 8 yields an instantaneous velocity of exactly 44 meters per second. This calculus operation transforms a sequence of discrete positions into a continuous model. While empirical data provides the starting point, the derivative lets us move beyond observed snapshots and calculate the exact vector state for any requested microsecond. The foundation of modern kinematics requires strict discipline. We cannot analyze physical reality using ignorant scalar distances. We have to rely on direction-aware state vectors. This flowchart demonstrates how these state vectors form a unified hierarchy of motion. We begin with position, and by applying the derivative operator with respect to time, we descend directly to instantaneous velocity. Moving to the final step of the kinematic ladder requires running the exact same operation. By applying a second derivative, measuring the rate of change of our velocity, we extract instantaneous acceleration. Replacing algebraic averages with mathematical limits frees us from relying on broad past observations. We no longer have to wait for an object to cover a measurable distance over time to understand what it is doing. By combining state vectors with the infinitesimal limit, we transition from observing motion in broad averages to defining it at its most granular level. This provides the mathematical framework required to accurately map any system moving along a one-dimensional path.